Imagine standing in front of something so hot, it could melt metal instantly, vaporize rock, and strip the electrons from every atom around you. Not lava, not the sun. I'm talking about temperatures millions of times hotter than anything naturally found in our solar system. And here's the wildest part. Humans have actually made it here on Earth. For a moment so short you couldn't blink in time to see it, we reached heat levels that existed only in the first heartbeat of the universe. But how hot was it exactly? And how did we do it without blowing up the planet? First, let's warm up your imagination. A candle flame burns at about 1,000 degrees Celsius. Lava flowing from a volcano? Around 1,200 degrees Celsius. The surface of the sun? 5,500 degrees Celsius. Even the sun's core, where nuclear fusion happens, is about 15 million degrees Celsius. Sounds intense, right? Here's the crazy thing. Those numbers are nothing compared to what's coming. But just how much hotter could we possibly go before physics itself breaks? When scientists measure extreme heat, they use kelvins. 0 Kelvin is the coldest temperature possible. Absolute zero, where atoms stop moving. On the other end, there's something called the Planck temperature, about 1.4 times 10 to the 32nd kelvins. The theoretical upper limit where the laws of physics as we know them collapse. Are we close to it? Not even remotely. But we've gotten shockingly far up that scale. The record-breaking moment came in 2012 at CERN, home of the Large Hadron Collider, the most powerful particle accelerator on Earth. Deep underground, scientists accelerated lead ions to 99.9999991% of the speed of light and smashed them head-on. Now, what do you think happens when two chunks of matter collide at almost the speed of light? The answer is stranger than you'd expect. The impact was so energetic that it created a droplet of something called a quark-gluon plasma, a form of matter so hot that the building blocks of atoms themselves melt apart. That means protons and neutrons, normally bound tightly together, literally dissolve into their fundamental components. And the temperature? About 5.5 trillion kelvins. Yes, trillion, with a T. That's roughly 100,000 times hotter than the sun's core. At this point, you might be thinking, could anything in nature be hotter than this? Hold that thought. We'll come back to it. For now, here's the catch. This plasma only existed for a few trillionths of a second before cooling. We didn't just create the hottest thing in human history, we also made one of the briefest events imaginable. And believe it or not, this wasn't the first time scientists got close. In 2010, at the Relativistic Heavy Ion Collider in New York, a similar plasma reached about 4 trillion kelvins. Still unimaginably hot, though slightly cooler than CERN's record. But here's the twist. Outside of particle accelerators, researchers are chasing another kind of extreme heat, one that can be sustained for much longer. I'm talking about fusion energy, the process that powers the sun. In a fusion reactor, you need temperatures in the hundreds of millions of degrees to force atomic nuclei to merge. China's East Tokamak, nicknamed the Artificial Sun, recently hit 150 million degrees Celsius and held it for over a minute. That's 10 times hotter than the sun's core, but still millions of times cooler than our trillion-degree particle collisions. So, which is harder to achieve? A brief trillion-degree flash or a sustained 100 million-degree burn? The answer might surprise you. Before we get to that, quick thing. If you love exploring the limits of science and want to see more deep dives into the extremes of the universe, hit that subscribe button and turn on notifications. That way, you won't miss our next journey into the impossible. Now, why would scientists even want to make something 5.5 trillion kelvins? After all, you can't cook with it, you can't stand near it, and you definitely can't put it in a lab oven. The reason is simple but profound. In the first microseconds after the Big Bang, the entire universe was a quark-gluon plasma. By recreating it, we can study how the universe cooled and formed the matter we see today. And here's where it gets even more intriguing. What if by making these conditions we stumble upon new physics? Maybe particles we've never seen before, or forces that don't exist at lower energies. This isn't just about breaking records, it's about peeking into the earliest chapter of reality itself. There's also the practical side. The technologies developed to reach these temperatures, superconducting magnets, precision detectors, ultra-high vacuum systems, often find uses in medicine, industry, and computing. And the research overlaps with the quest for fusion energy, which could one day give us a nearly limitless supply of clean power. So here's your answer. The hottest temperature ever reached by humans is about 5.5 trillion kelvins, achieved at CERN in 2012. For a blink of cosmic time, we match the heat of the universe as it was at its birth. But here's the real question. Is that the limit? Could future experiments push even closer to the Planck temperature? And if they did, would we discover entirely new forms of matter, or even create tiny black holes? Those questions remain open, for now. But given how fast we're advancing, the next record might be closer than you think. And if you think extreme heat is impressive, wait until you hear about the opposite extreme. The coldest temperatures humans have ever created, where atoms slow to a crawl and the rules of quantum physics take over. That's a story for another video, and trust me, you'll want to see it.